Okay, so quick recap of the unit vectors. So we're starting with this just because we have to start with something, and well, it's canonically or just by convention we start with this, with basis vectors. Okay, and next, see that this one is moved over here, and we replace the second search direction. Okay, and then in the third time, this again is moved over here, and we get something new here based on our results. So we are always updating our search direction. So in this case, we are starting search first in X, then in Y, okay? Get a new point. And then we are searching in first, well, Y direction, so I guess, up. So next we are first searching in up. And then this is, so, okay. And then in this direction, it looks like. And then based on that, maybe we're searching more to begin with. Well, next one, we will search first in this direction, and then maybe next time we will search in this direction. And then you see it kind of narrows down, so we're kind of just searching in one direction, and that's when these two vectors here are linearly dependent, meaning that you can't really span R2 with them. You can only go in one direction. And that's when the Powell method stops, or the naive Powell method stops. If you read pages 4, page 440 to 441, there's an improved Powell method where you basically recycle these vectors when they're close to becoming linearly dependent. Okay, did that clear something up? So you're in the Powell method, you're basically just refining the search direction on an assumption that since I'm already going in this direction, maybe I should just continue going in the same direction. It could also be catastrophically wrong to do that. And hopefully, if I have time, I'll do a demonstration of all of the methods I'm going through today. But gradient methods. Okay, I try to illustrate them here. The idea. It's kind of similar, but we use a search direction pk. pk from the point okay, which is the point we're at, for new point x plus 1 such that, well, we're looking for a minima, so x of k plus 1 should be less than f of k, like so. And again, the distance we have to travel along this gradient is again, well, golden search or bracket searching. Can be found solving the one-dimensional problem. Min alpha should be larger than 0 by convention. F x k alpha p k, like so. So then how do we find this search direction? Any suggestions? It's kind of in the name. But let's try to prove why pk is the best, or well, the gradient is a good search direction. So we can try to tail expand this. Oops. Have that x point k. Alpha here is just a scalar, so just a number. These are vectors. Tail expansion. So f k alpha p k post, and then f for the gradient of x. So, and then we can also do more, which we will do later. Alpha squared k p Hessian, or second derivative of xk of pk as well. So this bit here is called the Hessian, which we'll look at later. Hessian matrix. In this simple gradient search method, we will only look at this. Now we'll just disregard this, and then of course this. So looking forward, I will disregard this and only look at this. Okay, so how do we minimize this? Write this with some words. So if we just disregard again this bit and just look at this, then this is the rate of change of f of x in the point p. No, sorry, it's the function f of x in the point x, xk in the direction pk. Okay, and the rate of change is going to be this alpha here. I'm trying to write this in words. Rate of change in f, so the function f along the direction pk Okay. Is this coefficient alpha. That is looking at this. So, so now we'll look at the unit direction, pk. Most rapid descent or change, increase. Solution of problem. Minimize. The minimal direction here. And then the gradient. Okay. All the way. And here we are assuming P is a unit vector, meaning that the norm of P is 1. Because now we're only looking for the direction, and then it's easier if you just say that, oh, the direction, or the length of the direction is 1. Hence the word unit direction, P. Just means that this is going to be 1. It's just an assumption we make. Okay, so what is the minima of this function here? When P is 1? Well, so these are 2 different vectors. Right here. F. Well, you can just look at the inner product of them. So you have 2 vectors. What's the kind of inner product of them? Well, we can look at the okay, so I'm just gonna rewrite this. There. So this is what we're looking at. Delta. No, now F. Okay. This is what we want to minimize. And we know that this is a unit vector. Okay, this is also an inner product. And if you remember back to calculus, you know that the inner product of 2 vectors, that's the length of them times the angle between, or the cosine of the angle between them. Same as times the length of the gradient theta. Okay, and we know that this is 1. We don't care about the length here. We can't do anything about this. Now we can only do something about the angle between them. So what's the lowest we can go? Lowest of theta. The minimum of cosine of theta. Yes. So we get that P plus P minus going to be unit vector, it's going to be f of divided by the length of it. P. Oh, no, when you see, so this is a unit vector, so I think because I actually don't know the rule why. I can't think on the spot right now, sorry. But yeah, it's something to do when you divide by this. The Yeah, it's just algebra. I don't remember the name of it now. But anyway, this is just to prove that the optimal search direction is the opposite direction of the gradient. So the gradient shows the rate of change in positive. So we want to go the opposite direction of the change. Okay, so do I have something I can use here? Cup. Maybe. Do we have a, we have a ball. Cool. So if you're at the point here, then we can have the gradient. That's just a tangent line. Okay, and the gradient will point upwards in this direction. And if we want to go downwards, we're supposed to go the other direction. This is a sphere now, so it's a bad representation, but we're going the opposite side, opposite direction of the gradient. That's the optimal search direction if we disregard the Hessian and also the higher terms in the Taylor expansion. Yeah? Oh, there's no difference in them. This is just, I'm trying to argue why we should look in this direction. Yeah. Oh, because we are looking to minimize this function here. We're looking to minimize this function here, and the least we can go is when. So okay, we're looking for the inner product of this p we don't know the direction of, and the gradient. Okay, and the inner product we can write that as the norm of both vectors and then the angle between them. And well, cosine of theta, the lowest we can go with that is -1. So then it becomes pt. Can write it out in better. Let's see. Maybe I'm going too fast. But looking at what we have here, we see that we have p post delta. Okay. -1. And we will get change it over. Yeah. Okay. So yeah. I mean, what to take home here is that the optimal direction is opposite the search direction. Now, the optimal search direction is opposite the gradient. That's kind of like a detour. Then we will look at the steepest descent, which is what I try to motivate now with the P. Again, we need an, I guess you can kind of guess what's coming now, but start with an initial guess, 0. So then we evaluate the gradient in this point and compute the direction. Okay, so what did I do? Yeah, this is just notation. I'm just tired of writing f of xk, so I'm just going to write fk. This means f evaluated at the position xk. Yeah, just to save some space, or bulk, or whatever. And then we compute the next step. And we have to see if we are close enough. So we have to perform a convergence test. And we've been through some convergence tests earlier. So what could be a convergence test? Any suggestions? No? We could set a maximum amount of iterations. That's boring though. Or we could look at the distance between either two previous, the current and the previous function evaluation, or just the position. Those are the common convergence tests. So 1, maximum amount of iterations. Actually, it's very good to have a maximum number of iterations as kind of the last fallback, because you don't want your program to just run forever. So always have this in place. So it could be that you're not able to find a minima point. Second is we can require that the distance so of x k minus f of k plus 1 less than some number. So we see that when the function is changing very slowly, then we can say that, well, we're done, found the point. Or the last one is that if our 2 points, x k plus 1 minus, so the distance between the points is small enough, less than some kind of number, epsilon. And epsilon and gamma, we just pick them as small numbers, but not too small because maybe we can't obtain that kind of accuracy. So they should be small enough. So when you have a good enough solution, we have a good enough solution. But again, this method can be improved. And later we will look at something called the conjugate gradient method, which you can, so the conjugate gradient method, it's kind of a hybrid between Powell's method and the steepest descent, meaning that we exhaust different gradient or dimensions after a while. So conjugate gradient, usually you say that it's a iterative process, but mathematically speaking, you will always exhaust the iterations after the dimensions. I mean, in a two-dimensional problem, you can only do 2 dimensions of conjugate gradient, and you will be there. In steepest descent, you can do an infinite amount of iterations and still not be there. In the worst case. But some drawbacks or caveats of steepest descent. So many iterations. And also there are better. Pagata. When you get gradients, e.g. Think Powell, but with gradients. And also, since we're searching a line here, we also have the problem of, are we in a local minima or are we in a global minima? What's the difference? Well, this is a function. So then global minima. We don't know where we are. I mean, this is just a 1D function. I mean, we can graph it, that's fine, but when you have higher dimensions, it's difficult to know if we are in which of them we are. I mean, if we start the steepest ascent up here, well, then we're going to end up here. If we start here, also there, and if we're lucky and start here, we're going to find the global minimum. So we could try to just start with its different initial guesses, so different x zeros, and see where we end up. And in words, all line search methods are local methods. And there are different ways of actually finding the minima. You have something called annealing and lots of fancy ways of doing it. But you won't be looking at it. We will only be looking at the, well, simpler ways of finding the minima. And then, well, due to this, the starting guess and do we know that we are close? We don't really. So these methods aren't foolproof. You need to kind of know what you're doing before you use them, or else it could go wrong. It could go really wrong. So I'll quickly do Newton's method and then try to show. So I try to illustrate it with the Taylor expansion of the function, that you also get something called the Hessian. If we use the Hessian, we get the Newton method. So again, our Taylor expanding, but I'm going to skip the alpha this time. Plus dt delta of x of pt a pk. And I'm going to call this beast m, mk of p. And this beast, that's the Hessian, which is a matrix. And it could also be difficult to H of x equals. So yeah, I'm gonna write the general expression first and then do a 2D example. So it's going to be a matrix with a double derivative or partial derivative of f at point x, then by coordinate xy and xj. I j equals 1 up to the dimension we have, like so. In 2D, so if f of x equals y, the Hessian at point x, well, it's this thing, the where f x dx where f dx dy f y dx and dy dy. And if that is a lot to write, we have a shorthand notation of this. We'll also use later. This is basically f x x f x y x y x at x and f y y x. Again, just a shorthand notation. Okay, but that was kind of a detour. So what will be the direction to search for in Newton's method? Well, we basically want to minimize this mk. So this thing. Find a search. k, which is can't even read my own notes. To find the search direction, we find the p, of course, that minimizes m. Matrix or what? Okay. Okay, which these that we are looking for when the derivative of this m expression 0, meaning that we get delta f k plus delta, no, nabla, I guess, del f k p, and we will stop there. This equals 0, and the p that minimizes this, say pk that minimizes this, is minus the inverse Hessian, so minus 1 times the gradient of fk. So here we have two problems. Okay, it's more when you first have this Hessian and the Hessian and the gradient. Yes, you will find the minima quicker or in less iterations, but actually calculating the Hessian, that can take a while for larger systems or, well, higher dimensions. And then you also have to invert this matrix, and that is computationally expensive. And I see I won't be able to show you, or do you have like a couple of minutes? No? More lectures? Okay. Then I'll just point you where to look. So I've made some illustrations of how these methods work, which are available to run in MATLAB at GitHub. Username /EPG 4155. Oop. Take a look at those. It's in the optimization folder. They can play around with some different functions. See how they work.